What would happen if there were a moon so strange that its orbit seemed to obey no rule at all, far beyond the last planet where the sun is only a faint spark in a black sky? Pluto drifts quietly through darkness with its unseen companion. From a small flaw on a blurred photograph, Charon appeared more than just a satellite. It became a clue to a deeper mystery. Could this frozen pair hold the key to the solar system's secrets, and to the icy archives of the Kuiper Belt? From that imperfect image, the story unfolds: the discovery of Charon, the hypothesis of a double planet, the debate between violent collision and a slow cosmic kiss, the traces of a vanished ocean, frozen volcanoes, and the crimson stain at its pole. The trail continues outward to the Kuiper Belt to Arrokoth, and to Pluto's heart of nitrogen ice, all illuminated by new horizons. In this journey, we will explore the enigma of Charon, Pluto's largest moon, and uncover how this quiet companion may hold one of the final keys to understanding our solar system. At the frozen edge of our solar system, 6 billion kilometers from the warmth of the sun, a dim speck drifts through silence. For decades, Pluto had been nothing more than a blur of reflected sunlight, faint, stubborn, almost imaginary. Then, one ordinary June night in 1978, an astronomer named James Christie leaned over a set of photographic plates and noticed something that refused to behave. Pluto was not a perfect dot. It bulged like a breath caught halfway through a sigh. At first, the explanation seemed simple: a tremor in the atmosphere, a misaligned mirror, a slip of the lens. Every astronomer knew how easily Earth's own restlessness could blur the heavens. But Christie kept staring. The background stars were razor sharp. Only Pluto shimmered as if it were dragging a shadow of itself through the emulsion. He marked the image not to discard it, but to wonder. Days turned into weeks. He returned to older plates yellowed with time, each stamped with the word defective. One by one, the same strange swelling appeared, sometimes on the left, sometimes on the right, dancing around Pluto in a slow, patient rhythm. Christie began to measure the movement frame by frame. Every 6.4 days, the bulge completed a circle. The period matched Pluto's own rotation. Coincidence or choreography? The data whispered a hypothesis: the ghost was real. Some unseen companion, gravitationally locked, was orbiting in perfect synchrony. Two bodies bound in an eternal stare. A double heartbeat at the edge of sunlight. He brought the evidence to his colleague Robert Harrington. Together they tested every alternative instrument, error plate, defect, atmospheric distortion, until none remained. The signal held steady. The motion was precise, repeatable, mathematical. The ghost had mass. When at last the discovery was confirmed, it received a provisional name, S, 1978 P1. But Christie chose something quieter, more human. He named it Charon after his wife Charlene, and by mythic coincidence after the ferryman who guides souls across the river of shadows to Pluto's realm. Science and story folded into one. That night, as the observatory lights dimmed, Christie stepped outside. The Arizona air trembled with heat, yet above him the stars burned cold. Somewhere in that distance, a tiny world was pulling at another, carving invisible arcs in the dark. What began as a flaw on film had become the first sign of a deeper order, proof that even mistakes can reveal the hidden symmetry of the cosmos. He had the outline of a ghost. Now he needed proof. James Christie knew that astronomy is full of false alarms. A faint smudge here, a stray reflection there, a trick of atmosphere or chemistry that mimics something extraordinary. So before he could claim a new moon, he had to try very carefully to prove himself wrong. He started with the most mundane suspects. If the telescope were misaligned, everything on the plate would smear in the same direction. But the background stars were still perfect points, steady and sharp. If the atmosphere had shimmered, the distortion would be random from night to night. Yet the strange bulge near Pluto was orderly, returning again and again in a slow, patient arc. He turned to the archives. In drawers of old glass plates, some labelled poor or elongated image, Pluto appeared again as an imperfect dot. Most people had dismissed these plates as mistakes. Christie, now suspicious, measured them one by one. On each plate the bulge had shifted position as if an invisible companion were circling around Pluto. When he plotted the angles against time, a pattern emerged. Roughly every 6.4 days the ghost came back to the same place. That number mattered. Pluto's rotation period, its day, was already known to be 6.4 Earth days. The bulge was not drifting randomly. Whatever was causing it was locked into the same rhythm as Pluto itself, as if the two were turning together, always showing each other the same face. Christie shared his measurements with his colleague Robert Harrington. They checked the scale of the images, the calibration of the telescope, the timing written on the plate edges. They tested the possibility of a double exposure, a processing flaw, a chemical streak. Nothing accounted for a repeating 6.4-day cycle that matched Pluto's spin so precisely. The simplest explanation was also the boldest. There was another body there. Using the apparent separation between Pluto and the bulge on the plates and the period of the orbit, they could sketch a rough path, a tiny ellipse traced in the darkness. It was not yet a photograph in the modern sense, but it was enough to show that the ghost moved as a moon should move, circling its primary in obedience to gravity and geometry. In 1978, the discovery was announced. The new object received a temporary technical label, thus 1978 P1, the first satellite of Pluto found that year. Other observatories turned their telescopes toward the distant world. They too saw the subtle wobble confirm the periodic shift, watched the ghost complete its patient rounds. What had begun as a nuisance on a few bad plates had become a recognized member of the solar system. Years later, in 1986, the International Astronomical Union formally adopted the name Christie proposed Charon. Once it had been a smear on glass. Now it was a world with a name, an orbit, and a story. In the quiet of the observatory, amid the ticking of clocks and the gentle hum of instruments, a simple truth settled in. Sometimes, to find something new in the universe, you don't need a bigger telescope. You just need to look again at the things everyone else has already thrown away. When Charon stepped out of the photographic shadows and into the realm of confirmed objects, it did more than add a new moon to the solar system. It tipped over a line of numbers that astronomers thought they understood and quietly asked whether Pluto was really just a planet with a satellite, or something stranger. Once the orbit of Charon was known, its distance from Pluto and its 6.4-day period, astronomers could finally apply Kepler's laws to the system. From the way the two bodies moved around each other, they could estimate their combined mass. The answer was surprising. Pluto was far lighter than many had imagined, only about 1/6 the mass of Earth's moon. Charon, on the other hand, was unexpectedly hefty, roughly 12% of Pluto's mass. That ratio changed everything. In most planet-moon systems, the planet utterly dominates. Jupiter, Saturn, Earth, even Neptune all hold their moons so tightly that the shared centre of mass, the barycenter, lies deep inside the planet itself. The planet hardly shifts. The moon does all the obvious circling, but with Pluto and Charon, the barycenter is not buried within Pluto. It floats in the empty space between them outside the body of either world. If you could watch from afar, you would not see a big planet sitting still while a tiny moon loops around it. You would see two worlds circling a point in the dark like dancers holding hands and turning around a spot in the air between their palms. Neither is fully in control. Neither is merely a passenger. This dynamic led some scientists to propose a bold reclassification. Perhaps Pluto and Charon were not simply planet and moon at all, but a true double-planet system. In that view, Pluto is no longer the central figure with a subordinate companion. Instead, both are principal bodies, gravitational equals in a shared orbit, turning together in a locked embrace. There were other details that made the system feel unusual. Both Pluto and Charon are tidally locked to each other. Each always shows the same face to the other forever. If you stood on one hemisphere of Pluto, Charon would never rise or set. It would hang in the same place in the sky, shifting only in phase. On the opposite side, you would never see Charon at all. Two worlds fixed in a mutual gaze that has lasted for billions of years. As astronomers debated definitions in the early 2000s, trying to decide what should count as a planet in a solar system, suddenly crowded with Pluto-sized objects in the Kuiper Belt, this strange partnership lay at the heart of the argument. In 2006, when the International Astronomical Union met to formalize a new planetary definition, one proposal explicitly suggested recognizing Pluto and Charon as a double planet. In the end, the wider decision to reclassify Pluto as a dwarf planet overshadowed that idea, and the term double planet was set aside, at least on paper. Yet the physics remains. Titles can be changed by a vote, orbits cannot. Whether we call Charon a moon or a co-equal partner, it continues to tug on Pluto, and Pluto continues to answer both of them, circling their shared barycenter in the cold. Names and categories are human inventions. The dance is not. At the edge of the solar system, far beyond the warmth of our arguments, Pluto and Charon keep turning two small worlds locked in a balance that quietly ignores our need to choose which one is more important. So how did such a strange system come to be? Once Charon was accepted as real, that question hung over every discussion of Pluto. Two worlds of ice locked face to face, circling a point in empty space between them. It looked less like a typical planet-moon pair, and more like the aftermath of a cosmic accident. The challenge was to reconstruct that accident from only the faint traces it left behind. For many years, astronomers favoured a familiar idea, the giant impact hypothesis. In this scenario, a large body in the early Kuiper Belt slammed into a young proto-Pluto. The collision would have blasted a cloud of debris into orbit, and that debris over time would have gathered into Charon. It was a comforting model, because it echoed the leading theory for the formation of our own moon. We already knew such violent impacts could happen. Scaling the story down to Pluto and Charon seemed natural. On paper, the giant impact solved several problems at once. It explained the high angular momentum of the Pluto-Charon system, the nearly circular orbit, and the tight coupling between the two bodies. A single dramatic event in the distant past and the present-day dance would fall neatly into place. But as simulations improved and our understanding of icy materials deepened, the cracks in this picture began to show. Unlike early Earth, Pluto and Charon are not mostly molten rock. They are small rigid worlds made of a mixture of rock and a great deal of water ice. Under extreme impact conditions, ice does not behave like glowing magma. It shatters, vaporizes, and can be stripped away altogether. High-speed collisions between icy bodies tend to produce rubble, not two intact worlds with carefully preserved interiors. Yet observations suggested that Pluto and Charon had kept much of their internal structure. Pluto is denser with roughly 70% rock. Charon is lighter, around 55%. They do not look like the thoroughly mixed remnants of a single shattered object. They look more like two separate worlds that somehow became bound together. Out of this tension, a new idea emerged. Instead of imagining a catastrophic smash, some researchers began to simulate a low-velocity grazing impact, less an explosion, more a near miss that wasn't quite a miss. Two proto-worlds approaching each other slowly in the cold Kuiper Belt clipped together and stick forming a temporary snowman-shaped body. For a brief time, they spin through space as one joined at the hip. Then, under the pull of tides and rotation, they pull apart again, stretching into two distinct objects that remain gravitationally bound. This cosmic kiss or kiss and capture scenario has an elegance the older model lacks. Because the impact is gentle by cosmic standards, both bodies can survive largely intact. Their different rock-ice ratios make sense they formed separately and were never completely mixed in a fiery collision. The resulting orbit naturally places the barycenter outside Pluto, matching what we see today, and the immense tidal forces during that brief tangled union would have pumped heat deep into both worlds, melting internal ice and perhaps creating subsurface oceans. No one witnessed this ancient encounter. We reconstruct it from mathematics, from computer experiments, from the quiet clues written into densities and orbits and scars on frozen crusts. The universe does not replay the event for us. It leaves a puzzle and invites us to see which story fits the pieces best. The debate is not entirely finished. Science rarely offers a perfect ending. But as models grow more detailed, the low-velocity kiss continues to match the data with remarkable grace. It takes Pluto and Charon out of the realm of simple impact debris and into something more intimate. Two wanderers who met, collided softly, and were never fully parted again. Far from the sun, where time stretches and change is slow, that brief embrace may have set the course for everything that followed the tearing of Charon's crust, the possible birth and death of hidden oceans, and the quiet, eternal dance we see today. To understand the geology of these worlds, we must first understand the moment they became a pair. For 37 years after its discovery, Charon was little more than a rumour of a world, a moving blur beside Pluto, a set of numbers in an orbit table. Even with telescopes pushed to their limits, its surface remained unresolved, its features smeared into anonymity. That changed in July 2015 when NASA's New Horizons spacecraft swept through the Pluto system at over 50,000 kilometers per hour. For a handful of hours, the probe threaded a path past Pluto and its moon, turning its cameras toward that distant icy double act. Then, for the first time, the ghost gained a face. The images that returned from the edge of the solar system were astonishing. Charon was not a smooth, sleepy lump of ice. Its surface was scarred and sculpted, marked by a violence that seemed out of place in such a small, cold world. Most striking of all was a belt of canyons and faults that wrapped almost all the way around its equator, great gouges in the crust running for at least 1/800 kilometers and plunging up to 7.5 kilometers deep. By comparison, Earth's Grand Canyon suddenly looked modest. These fractures are not random. They form a network of extension places where the surface has been pulled apart, stretched like a skin that no longer fits the body beneath it. For geologists, that pattern is a clue. On a small icy moon, you do not need plates colliding or continental drift to make chasms on a global scale. You need something inside that has expanded and forced the outer shell to crack. Here the formation story of Pluto and Charon returns in a new guise. If a gentle cosmic kiss and the subsequent tidal struggle between the two worlds injected heat into Charon's interior, much of its water ice could have melted, forming a subsurface ocean trapped beneath a rigid crust. As long as that ocean remained liquid, the crust would stay more or less in place. But ice and water do not share the same volume. When liquid water freezes, it expands. On a planetary scale, that change is not subtle. As Charon slowly radiated its heat into space over hundreds of millions of years, the hidden ocean would begin to freeze from the top and bottom. Layer by layer, what was once a global sea turned to solid ice. The interior swelled. The rigid outer shell, unable to stretch smoothly, responded the only way it could: it split. Long faults opened, cliffs rose, valleys sank, and the equatorial canyon belt was carved in silence. New horizons also revealed broad, relatively smooth plains in some regions, and older, heavily cratered terrain in others, hinting at episodes of resurfacing and long pauses in between. Taken together, the fractures, the plains, and the pattern of craters tell a story of internal change rather than external bombardment. The primary sculptor of Charon's face seems to have been its own interior warming, melting, freezing, and relaxing over eons. We cannot drill through that frozen crust. We cannot sample the ancient ice directly. All we have are the shapes on the surface and the physics that govern ice rock and gravity. But when we run the numbers, the scenario holds together. A warm beginning, a buried ocean, a slow freeze, a world pulled apart as it cooled. Today Charon appears geologically quiet. No current eruptions, no obvious tectonic motion, nothing to suggest that the deep interior is still restless. It is a snapshot taken long after the drama ended, like a cracked lakebed after the water is gone. Yet those immense canyons frozen in place carry the memory of a time when this small moon was changing fast, reshaping itself from the inside out. At the edge of the solar system, far from storms and sunlight, New Horizons found evidence that even modest worlds can live through great internal dramas. Charon's fractures are not just scars. They are signatures, lines written in ice that confirm the invisible history suggested by our theories. Where numbers once hinted at heat and motion, the landscape now quietly agrees. When New Horizons sent back its first close-up portraits of Charon, scientists realized that the story written on its surface was even more complicated than a world torn open by a freezing ocean. There was quite clearly another layer. The spacecraft revealed a moon divided in two. To the north lay Terra, an old battered highland, rugged and heavily cratered, its landscape crisscrossed by the great tectonic scars carved when Charon's interior expanded and the crust ruptured. This was the original skin of the moon, fractured but preserved a fossil of the ancient cataclysm. But to the south, the world changed. Here stretched Vulcan Planitia, a vast, low-lying plain that looked almost tranquil by comparison. It was smoother, softer, far less cratered than the northern hemisphere. Crater counts, our way of telling planetary time, suggested that Vulcan Planitia was much younger. Something had resurfaced this region long after the great tearing of the crust. The texture of the plain held clues: broad, gently undulating swells, subtle ridges, and what looked like frozen flows hinted at motion not from above but from below. This was not simply a patch of ice smoothed by erosion or blanketed by falling debris. It looked poured. Planetary geologists began to speak of cryovolcanism. Volcanoes not of molten rock, but of chilled slush. In a world made largely of water, ice, ammonia, and other volatile substances, magma takes a different form. Deep beneath the crust, as the subsurface ocean froze and expanded, the remaining liquid could have been trapped under increasing pressure. Mixed with ammonia and antifreeze that lowers the melting point of water, the cryomagma would remain liquid longer than pure water, even as the surrounding layers solidified. Eventually, the pressure would become too great. The same fractures that split Charon's crust could also act as conduits. Through these cracks, the pressurized cryomagma would surge upward, erupting onto the surface as floods of icy slush. Spreading out under low gravity and bitter cold, these flows would gradually freeze in place, forming broad, smooth plains, the very face of Vulcan Planitia we see today. Scattered across this frozen sea stand isolated mountains such as Kubrick Mons, towering stacks of ice that appear to sit in shallow depressions like islands trapped in drained lakes. One compelling idea is that these are enormous blocks of the older northern crust that broke away were lifted and carried along by the cryovolcanic floods, then left stranded as the flow solidified around them. Icebergs not on water, but in ice itself. Yet even with these elegant explanations, questions remain. How long did the cryovolcanic activity last? Was it a single world-spanning episode or a series of pulses, each adding another layer to the southern plains? Did the eruptions tap directly into the last remnants of Charon's subsurface ocean, or into pockets of melt generated later by radioactive decay in the rocky core? From a distance of billions of kilometers we can only infer. We read the direction of frozen flows, map the heights of stranded mountains, and simulate how mixtures of water, ammonia and salts might behave in Charon's weak gravity. The picture that emerges is persuasive but not final, a world that after tearing itself apart tried to smooth over half its face with slow cold floods from within. Today Vulcan Planitia lies still its cryovolcanoes, if that is truly what they were long extinct. But in the quiet geometry of its plains and the lonely silhouettes of its mountains, the memory of that strange icy volcanism remains, hinting that even in the farthest, coldest corners of the solar system, planets and moons can find ways to move, to flow, and to change. At first glance, Charon's North Pole looks as though someone has pressed a dark thumbprint into the ice. A broad reddish-brown stain caps the top of the moon, so striking that the New Horizons team nicknamed it Mordor Macula. Under the thin sunlight of the outer solar system, it glows faintly like dried blood on snow. Scientifically, the colour comes from Tholin's complex organic molecules created when simple gases such as methane are broken apart by ultraviolet light, and charged particles then stitched back together into darker, heavier compounds. But where did the methane come from? One leading idea points back to Pluto. In this hypothesis, Pluto's tenuous atmosphere slowly leaks methane into space. Some of that escaping gas drifts outward and is captured by Charon's gravity, settling preferentially at the frigid poles, where temperatures are lowest. There it freezes out as a thin layer of ice, then is steadily processed by radiation into the rusty Tholin cap we see today. A competing picture keeps the story entirely within Charon. In that version, methane once welled up from the moon's own interior, perhaps released during episodes of cryovolcanism, then migrated to the poles before being transformed. In both cases, the red stain is a memory either of Pluto's breathing atmosphere or of Charon's inner fires quietly preserved at the top of the world. Far beyond Neptune, where the sun is only a bright star in a black sky, there is a region that astronomers once knew only as a suspicion. For much of the 20th century, Pluto seemed to stand alone out there, small, strangely tilted on an elongated path that cut across the orbits of the giant planets. Something about that loneliness felt wrong. Pluto's orbit is eccentric and inclined as if it had been nudged or shaped by neighbours we couldn't see. Its size, too, was puzzling. For a time, some hoped it might be as large as Earth, then as big as Mars, but better measurements shrank it down to a modest dwarf. Too small, perhaps, to be the sole ruler of the outer frontier. Its behaviour suggested it was part of a crowd, not a solitary king. In 1951, astronomer Gerard Kuiper gave form to that unease. He proposed that beyond Neptune there might exist a broad belt of icy bodies, ancient remnants of the solar system's birth never gathered into a single planet. Without instruments powerful enough to detect such faint, distant objects, his idea remained a theoretical sketch, a ghostly ring drawn in the dark. Still, the hypothesis lingered. Comets with short periods returning again and again on tight loops seemed to come from somewhere just beyond Neptune. Their icy compositions and orbits hinted at a reservoir of frozen debris, a kind of celestial attic where the early building blocks of planets had been stored and forgotten. Pluto and its newly discovered moon Charon would later be recognised as residents of that realm. But in the early days, the Kuiper Belt was only a whisper, an invisible structure inferred from clues, a possible answer to the question of why Pluto was so small, so oddly placed, and perhaps not as alone as we first believed. To understand the Kuiper Belt, it helps to trace our way outward from home step by gentle step. begin near the Sun where light is fierce and shadows are sharp. We drift past Mercury, Venus, Earth and Mars, the familiar inner worlds. Between Mars and Jupiter we cross the asteroid belt, a thin stony ring left over from planet formation. It lies about 2.2 to 3.2 astronomical units from the Sun and is roughly 1 AU wide. 1 astronomical unit, or AU, is the distance from the Earth to the Sun, about 150 million kilometres. Beyond the asteroids we pass the giant planets Jupiter, Saturn, with its rings, then the pale orbs of Uranus and Neptune. Neptune orbits at about 30 AU. For a long time that number marked the end of the well-mapped solar system, but if we keep going, something new appears. From roughly 30 to 50 AU space is not empty. Here stretches the Kuiper Belt, a broad, thick ring of icy bodies encircling the Sun like a frozen halo. It is far wider than the asteroid belt, and though its objects are scattered over an enormous volume, there are countless pieces dwarf planets like Pluto, Haumea, Makemake, Eris, and hundreds of thousands of smaller worlds more than 100 kilometres across. On average, the distance between neighbouring objects can be tens of millions of kilometres. They are solitary, each following its own slow path, yet together they outline the shape of the belt. From the vantage point of a spacecraft, you would not see a dense swarm of ice chunks. You would see one horizon after another of darkness, and occasionally, very occasionally, a small distant sunlit shard gliding by. Far beyond, perhaps starting around 2000 AU, and extending to tens of thousands of AU lies the hypothetical Oort cloud, a vast, almost spherical reservoir of comets. Compared to that, the Kuiper Belt is a relatively thin flat ring hugging the plane of the planets. It sits at a strange threshold, not quite the end of the solar system, but a quiet borderland where the architecture of our planetary family changes from worlds and rings to relics and fragments. Unlike the rocky shards of the asteroid belt, the inhabitants of the Kuiper Belt are made of gentler stuff. Most Kuiper Belt objects, KBOs, are mixtures of water ice, frozen methane ammonia, carbon monoxide and darker carbon-rich materials. They are more like dirty snowballs than stones preserved in deep freeze for billions of years. Some are only a few kilometres across. Others, like Pluto or Eris, are large enough to pull themselves into near spherical shapes, becoming dwarf planets with their own moons and weathered surfaces. Between these extremes lies a vast population of medium-sized bodies, hundreds of kilometres wide, each one a fragment of the primordial solar system. Because they are so cold and distant, chemical reactions crawl along at a glacial pace. Ices that would quickly sublimate closer to the Sun can survive here for the age of the planets. In that sense, KBOs are time capsules. Their compositions preserve the blend of materials that once swirled in the outer parts of the protoplanetary disk when the Sun was young and the planets were still assembling. It is tempting to imagine that long ago these scattered icy pieces might have come together to form another full-fledged planet. The total original mass of the Kuiper Belt may have been several times that of Earth. In a quieter neighbourhood, gravity could have gathered them into one or two distant giants of ice and rock. But the outer solar system was not entirely quiet. The migrations of Jupiter, Saturn, Uranus and Neptune especially. Neptune's slow outward drift likely stirred the region, scattering many planetesimals and preventing most from merging. Instead of one more large world, we are left with a swarm of smaller ones, remnants of a planet that never quite happened. Each KBO then is not just a frozen rock, it is a surviving piece of an interrupted story. The Kuiper Belt is not the final edge of order. Beyond its main band of orbits, the architecture of the solar system begins to fray. On the outer side of the belt lies a region known as the scattered disk. Here, many icy bodies follow stretched tilted paths, some carrying them hundreds of astronomical units from the Sun before they slowly fall back in. These objects are thought to have been tossed outward long ago by close encounters with Neptune, their orbits pulled into elongated loops like threads tugged from a woven cloth. Some of these scattered objects come as close as the main Kuiper Belt, then swing far beyond it out toward nearly 1000 AU. In this space, sunlight is faint and the Sun is no longer a dominant presence but a distant beacon. Gravity still binds but weakly. A small nudge, a passing star, the collective pull of the galaxy can over millions of years reshape a path entirely. Farther still, astronomers suspect the existence of the Oort cloud, a vast, roughly spherical shell of icy bodies that may extend from about 2000 to as far as 100,000 AU. We have not seen it directly. Its presence is inferred from the long-period comets that fall inward from all directions on orbits that can take millions of years to complete. If the Kuiper Belt is a ring, the Oort cloud is a mist, In this layered structure, main belt scattered disk distant cloud lies a subtle division of labour. Short-period comets, which return again and again on predictable timescales of years or decades, are thought to come primarily from the Kuiper Belt and scattered disk. Long-period comets, which may appear once in a civilization and never again likely fall in from the Oort cloud's remote reservoir. Together, these regions form a kind of extended shoreline. Closer in planets and dwarf planets, farther out fragments and snowballs barely tethered to the sun. Beyond that, only the slow tides of the galaxy itself. Standing here in thought, we are already at the threshold where our solar system begins to give way to the wider, deeper sea of stars. Today, the Kuiper Belt is a ghost of what it used to be. By most estimates, all of its present material adds up to only a tiny fraction of Earth's mass, far less than we would need to build a full-size planet. Yet models of the early solar system suggest a very different picture, a young Kuiper Belt that may once have contained 7 to 10 Earth masses of icy planetesimals. Somewhere along the way, most of that mass vanished. The leading hypothesis points to the restless migrations of the giant planets. In the Nice model and its relatives, Jupiter, Saturn, Uranus and Neptune did not form exactly where we see them today. Instead, as they interacted with the surrounding disk of smaller bodies, they traded angular momentum, slowly drifting to new orbits. Jupiter edged slightly inward. Saturn, Uranus and Neptune moved outward. For the fragile residents of the outer disk, this was like living beside slow-moving bulldozers. As Neptune pushed outward into the primordial Kuiper Belt, its gravity stirred the region, scattering countless planetesimals. Some were flung inward, where repeated gravitational kicks from the giants ejected them entirely from the solar system, sending them into interstellar space. Others were tossed onto highly elongated or inclined orbits, becoming part of the scattered disk or the distant Oort cloud. Only a minority remained in relatively stable low eccentricity paths, forming the quieter Kuiper Belt we see today. Collisions also played a role. In a denser belt, icy bodies would have struck one another far more frequently and at higher speeds. Some impacts would merge objects, but many would shatter them into fragments, grinding the population down over hundreds of millions of years. The smallest debris dust and fine ice grains could then be swept away by solar radiation pressure, or dragged inward by subtle forces like Poynting Robertson drag slowly bleeding material from the system. This gravitational stirring and collisional erosion provide a natural way to explain two things at once: why the Kuiper Belt is so low in mass today, and why it serves as a source of short-period comets. Objects nudged onto unstable or resonant orbits can gradually drift inward until they cross the paths of the giant planets, where further interactions send them sunward as comets, with periods of only a few years or decades. Each returning comet is a small reminder of a much larger population that was once out there. We cannot rewind the early solar system to watch this depletion unfold. Instead, we infer it from the present-day orbits and sizes of Kuiper Belt objects, from computer simulations of planetary migration, and from the steady reign of short-period comets that still visit the inner system. Together, they tell a sobering but elegant story. The Kuiper Belt we see now is a remnant thinned out by gravity and time, the surviving edge of a once crowded frontier. Before New Horizons, the Kuiper Belt was mostly a work of inference. We knew it was there from faint moving points on long exposures from the orbits of comets, from the way Pluto behaved. We could sketch its structure with mathematics and telescopes, but it remained in a very real sense theoretical, a carefully drawn map of a land no one had visited. New Horizons changed that. Launched in 2006, the spacecraft spent nearly a decade crossing the giant planet's realm and coasting into the deep cold beyond Neptune. On 14th July 2015, it swept past Pluto and Charon at enormous speed, coming within about 12,500 kilometers of Pluto's surface. For a few brief hours, it turned its cameras, spectrometers, and particle detectors toward the dwarf planet, its moons, and the surrounding environment, gathering more data than all previous observations combined. Those images and measurements did more than reveal beautiful landscapes. They were a direct test of our hypotheses. Pluto's complex layered atmosphere, its vast nitrogen glacier heart, and Charon's fractured resurfaced plains all confirmed that even small Kuiper Belt objects could be geologically active and internally differentiated. The idea that KBOs were simple inert leftovers had to be set aside. Our models of their composition and thermal histories needed to expand to account for oceans' convection and long-lived internal heat. After Pluto, New Horizons continued deeper into the belt. On New Year's Day 2019, it flew past 2014 MU69, later named Arrokoth, the most distant world ever visited by a spacecraft. Arrokoth's flattened, snowman-like shape, smooth surface, and gentle contact between its two lobes provided powerful evidence that some planetesimals formed through slow local cloud collapse rather than violent high-speed collisions. This directly addressed a long-standing debate about how the building blocks of planets first came together. In both flybys, New Horizons served as a kind of experiment to send an instrument into a predicted environment, then see whether reality matches the expectations. The mission did not answer every question, but it refined the story. The Kuiper Belt is indeed a reservoir of ancient icy bodies. Its objects do preserve early solar system conditions, but they are not static fossils. They are worlds with histories melting, freezing, colliding, and occasionally quietly evolving in the dark. From its lonely trajectory, New Horizons turned lines on a graph into places and transformed a distant hypothesis into a landscape we could almost imagine standing on. For decades, the question of how the very first building blocks of planets formed had two competing answers, and neither was entirely satisfying. In one picture called hierarchical accretion, the early solar system was a chaotic shooting gallery. Tiny grains stuck together to make pebbles. Pebbles grew into boulders and boulders into kilometre-sized bodies, all through countless collisions. But as objects grew larger, their mutual gravity made their encounters faster and more violent. At those speeds, impacts are more likely to shatter than to gently merge. It was hard to see how fragile, loosely bound planetesimals could survive such a brutal childhood. The alternative picture, local cloud collapse, imagined something quieter. Instead of endless high-speed impacts, clouds of small particles in certain regions of the protoplanetary disk would slowly clump together under their own combined gravity. Dragged by gas dust, could concentrate into dense filaments or patches. Once those patches became massive enough, they would collapse not explosively, but in a slow collective fall, forming a single larger body at relatively low speeds. This solved the violence problem, but was difficult to prove from far away. Then New Horizons flew past Arrokoth. Arrokoth is small, about 35 kilometers long, and shaped like a flattened snowman, two lobes gently touching their surfaces, remarkably smooth and largely unbroken by deep fractures. The contact between the lobes is narrow and neat, as if they drifted together and fused at walking pace. There is no sign of the crushing high-speed chaos you would expect if they had slammed together in a violent collision. Its subtle colour variations and nearly aligned spins suggest that the two lobes formed close together from the same cloud of material, then orbited each other in a tight binary, before slowly spiralling inward and merging. Everything about Arrokoth's structure whispers low-velocity, delicate assembly, careful collapse. When scientists fed these clues back into their models, the balance shifted. The hierarchical accretion scenario no longer seemed to be the main architect at these scales, at least not in the outer disk. Instead, Arrokoth stood as a quiet but compelling witness for local cloud collapse. Its very shape, preserved in the deep freeze of the Kuiper Belt, became a three-dimensional fossil of how some planetesimals were born. We still expect that both processes played roles in different places and at different times, but thanks to one small world beyond Pluto, the decades-long debate gained a strong, elegant answer. In the far reaches of the young solar system, many of the first building blocks of planets likely formed not through endless violent crashes, but through the gentle gathering and settling of dust and ice into clouds that fell in on themselves. In Arrokoth's frozen silhouette, we see the echo of that first quiet collapse. When New Horizons swept past Pluto, it gave us more than a quick look at a distant dwarf planet. It opened a window into the heart of the Kuiper Belt itself. The most famous image from that flyby is almost disarmingly simple: a small world against the blackness bearing a bright, pale heart. The region called Tombor Regio is split into two lobes. The western lobe, Sputnik Planitia, is a vast basin filled with nitrogen ice about 1,000 kilometers across and several kilometers deep, likely the largest known glacier in the solar system. Its surface is patterned with soft polygonal cells, slowly churning convection cells of frozen nitrogen that rise and sink over millions of years like an impossibly slow boil. Why is it there? Two main ideas compete gently in the background. One hypothesis imagines an internal ocean beneath Pluto's crust. In that scenario, a giant impact or an internal imbalance created a low spot. Over time, denser ice and liquid water shifted beneath pulling Sputnik Planitia toward Pluto's tidal axis with Charon. the basin filled with volatile nitrogen, and the whole region became a window where Pluto's hidden ocean subtly influences the surface. A newer hypothesis suggests that the heart's western lobe is itself the direct scar of a low-velocity oblique impact, a cosmic splat where an incoming body struck at an angle and left behind the elongated depression we see now. In this view, the glacier is both in fill and fingerprint its shape, dictated by the memory of the collision. Either way, the heart is not just a pretty pattern, it is the surface expression of deep processes, whether in Pluto's interior or in its collisional past. New Horizons has moved on, but our tools have improved. The James Webb Space Telescope now studies Kuiper Belt objects from afar, teasing out their surface compositions, temperatures and atmospheres in infrared light. Future missions may go further, an orbiter that lingers around Pluto and Charon, mapping their gravity fields to search for oceans, a probe that flies past multiple KBOs in sequence, perhaps one day a robotic lander that touches down on an icy plain and scoops up ancient material for return to Earth. We do not know which of these missions will fly or when, but the questions are now on the table, clearly framed by the data New Horizons returned. Pluto is no longer a lonely oddity at the edge of the map. It is a doorway, and beyond it the Kuiper Belt stretches out, waiting quietly for us to come back.